Hi, Elise. How you doing? You have 3 handouts, Elise? If you would, please. Okay, well, we've got 8:30, so why don't we get started? Good morning, S&P.
Good morning.
Wow, that's a terrific response, especially for a rainy Wednesday in the middle of week 9. So here we are, and we're going to be talking about depth perception today. And actually, we'll be talking about depth-related phenomena on Friday also. So look forward to having that conversation with you. And then we'll be coming up on exam 3 in just a week, but I'll say more about that in the sessions ahead. I did want to make one announcement, and that is that tomorrow afternoon we have a really exciting talk. This is given by one of our visiting professors, Dr. Rebecca Achtman is going to be talking to us, and you'll see these all around the department. She'll be talking to us about video game playing and how it actually improves attentional skills and visual skills. And this will go on in Burton Morgan's lecture hall at 4:30 tomorrow afternoon. We hope that you'll come out. We always encourage our psychology students to come to all psychology colloquia, and especially when one of our own faculty is going to be giving this. She's a neuroscientist, so I've been advertising to the nerds, encouraging them to come out as well, and I hope we get a really good turnout tomorrow. I think you'll find it really accessible and really interesting. I know that video games have sometimes gotten a lot of bad press. They're sometimes associated with violence and so forth. Here we get the better side of that story, that we can see some improvement in visual and attentional skills. So I hope you'll come out at 4:30 tomorrow, Burton Morgan Lecture Hall. Okay, how many people got a chance to watch the video for today? Yeah? All right, really good. What we'll do is start out just by talking of some of the monocular depth cues, and I referred to monocular depth cues in the video, and I thought what I'd start out with is first this piece, which I think is really quite interesting. And I'll turn down the light. We might get this a little bit more saliently if we see this picture, which is a flat picture. Show of hands, how many people are getting sensations of depth from this picture? Okay, isn't that really spectacular? Just what they're doing with the way the lines are contoured and so forth, I think presents a really compelling image of depth, even though we know that's only 2-dimensional. I feel like I could jump right into that hole and it would be a really, really deep hole. Great image there. How many of us have seen this so-called sidewalk art that's 3-dimensional? Okay. How many of us are less familiar with that, the 3-dimensional sidewalk art? Okay, a few of us have seen it, a few of us haven't. I'll turn the lights back up, and we'll take a look at some monocular depth cues by these tremendous artists. In a liberal arts education, we should try to engage the sciences as well as the arts. So let's go on over to here. Okay, and what you'll see here is, oh, maybe it's better when these are down. You get better contrast. Per the Michelson contrast formula, we get better contrast when the lights are down. So this person actually is on a sidewalk, or at least a flat surface, but it doesn't look that way. Right? I find these to be really, really compelling. We'll go down a little bit more. Take a look at another image. Okay. And the sidewalk artists are really clever. Look how far down that goes, right? Right? Okay. Here's an artist next to his work. It's hard to get all of that in there. Okay. Now at some point there's like 30 images here, and I haven't gone through all of them. I just went through the first several so we can see how compelling this is, but just the creativity is wonderful, and clearly these folks understand something about monocular depth cues in order to create all of these wonderful illusions for us. And every once in a while they'll show you 2 pictures. They'll show you maybe the best angled picture to get the depth effect, which you get here, maybe this waterfall, no, I guess it's a bird's wing kind of a thing. And then sometimes they take it from a different angle, and you see how distorted the pictures are in order for this to work optically at one particular viewing angle. I don't know how many artists there are here. I don't know if this is the same person. We see this recurring character. Right? Okay, maybe this is a really good example. I mean, it does look like he's standing on top of the world here. But then if you see that same thing from a different angle, you see how elongated it is. Right? Really, really clever. And these people truly understand the optics of the situation. Okay, maybe we'll make this the last one. Okay? So what a fun phenomenon psychologically, right, when we're talking about depth perception. And all of this can be done with even one eye's view, right, the monocular depth cues. I mentioned one other monocular depth cue in the video. Does anybody want to recall what that was? One other monocular depth cue? I'll put some lights back on so we don't put everybody to sleep. Thank you. Riella's got something. Occlusion, yeah. And so just can you say a little bit more about occlusion and how that works?
When an object is partially hidden by something, your brain just kind of like assumes that it's all one piece and it's not an outline of whatever is in front of it.
Okay, right. So we have something occluding something else. The occluder is typically seen as being nearer in depth, and that which is occluded is seen as being further in depth. Okay, so we get some relative depth position in the z-plane that we've been describing in the video, based on what is being occluded and what is doing the occluding. Right, so that would be a very salient kind of a cue. It's available to us even if we had only one eye. Now, a lot of folks have two working eyes, but they actually don't have the stereopsis that we mentioned in the video. They have instead two working eyes, but they actually can't synthesize the two images. It's something like maybe 5% or 10% of the population. And a lot of these folks don't know that they don't have stereopsis. It only comes to be known to them if you give them a fairly sensitive stereo test and they fail the test and they start to figure out, hey, I actually am missing some kind of perceptual skill that many people do have. But it's a surprisingly large fraction of the population, maybe on the order of 5%, that doesn't have stereopsis. Okay, when we're combining the information from the two eyes. Okay, so lots to do today. We'll go into some free fusing. Why don't we start out with that? So does everybody have the 3 handouts? And maybe we'll start out with this one. Okay, we can all grab the 3 handouts. And then we'll start out with that. And as I mentioned in the video, we're going to use this as our septum. We're going to use this to divide our left eye's view from our right eye's view. And why don't I put up a couple of images that might be most helpful for us. Okay, so something like this. Okay, and we'll stay with the top image. There are actually 2 images here. We'll be on page 1, and we'll look at this top stereogram. There's a bottom stereogram that we'll get to in a moment. Okay, and if you could first do this, if you'll take this, hold it long ways, just like this, and put it right between your eyes. If we all do that with me, okay? Okay, so now I've got my right eye going over here. This is my left eye. And now, if you would, and I'll do this along with you, would you please come along and put this right down on your page, right on that upper image, separating the left eye's view and the right eye's view. And you'll give yourselves a couple of moments. You shouldn't get too frustrated with this. June, we have 3 handouts there. Okay? You shouldn't get too frustrated with this. It'll take a moment. But if you relax your eyes and almost see if you can see through your desk down toward your feet. Try to relax your eyes as if you're trying to get all the way down to your feet. And what will happen is the left and right images will eventually slide toward each other. It'll be very gradual, and then you'll lose your focus and they slide back to where they were. You'll basically get them to come in. Okay? Okay, and at some point they become one. So Harshit has got a good phrase for that, right? They fuse. Okay? Now there are other ways. We'll do other kinds of fusion later on today. This is called free fusing because we're not using an optical device. A index card is not an optical device per se. We're using it as a septum. And we'll give you a moment to look at the top image. We'll ask you not to go to the bottom image just yet. For those of you who are having a little bit of difficulty free fusing and they're not quite coming together, what you might do is lift the index card a little bit off of the page and give your eyes just a little bit more distance from the stimulus, these geometric shapes, and that might make it a little bit easier. It might be the case that your eyes don't have to do quite as much vergence. How many people got that? Wow, okay, that's actually better than what I usually get. Usually I get about 3 in my entire class, and then after a few more minutes I get maybe a couple more people. And usually it's better this way than this way. If you do it this way, then you're a little bit too close to the page. If you give yourself a little bit more distance that way, it's easy. Okay, so can somebody, you can look at it again. If somebody can tell me, please, what you get when you're fusing the top image, and we'll stay on the top image, psychologically, what are you experiencing? I'll try not to lead the witness here. Okay, why don't we go with Chelsea?
You experience basically a fusing of the 2 pictures, as we said.
Okay.
And it looks like one box in the very center of the visual field, one of those boxes.
Okay, right, so these 2 become one. That's really good. Kirsten also had her hand up. Did you want to add anything to that, Kirsten?
It kind of looked like the oval was almost like 3D, like bouncing off the page.
Excellent. Okay, all right, so thank you for all of those observations. So Chelsea's saying this thing comes together. There are actually two of them out there in the distance, right? And they become one psychologically. I like what Kirsten had to say, and that is that there's this bouncing around, and specifically you mentioned that the oval is looking near to you in depth, okay? And this near-far distinction is something that we had a lot of information about in the video, and here we're getting something, I hope, that's relatively psychologically salient. How many people had that experience of the oval being near in depth, okay? The oval being near in depth. Before we take questions and comments on that, I wonder if we could just stay with this one more time, and I think it's the next image. If we go down to the bottom, can we do this one more time? We'll actually practice free fusing one more time. It's best to hold this lengthwise. Same ball game, but now try the bottom image. And you'll get them to fuse, as Chelsea said a moment ago. And hopefully you'll get some bouncing around of these images in depth. They won't be in the same depth plane. Kirsten said we had different depths. We'll see if you can figure out where they are relative to each other in depth on the bottom image. Anybody get a different? Okay, what did you get, Jenny? Yeah.
The rectangle shape was farther away in depth.
Okay.
Compared to the other two, we're still seeing kind of at that.
Okay, right. So this one, Jenny is reporting, seemed further away in depth than the other two, which seemed to be in the same depth plane as each other. How many people got that psychological experience? Okay. So what's really cool about this is if you were just walking in, and I asked you to pick up this handout because we have 3 handouts today, it might not have been entirely obvious that these would go on to generate very different depth effects. I mean, they look like pretty boring geometric shapes with the circle, the oval, and the rectangle, right? But just based on subtle retinal disparities that you learned about in the video, we can have very drastic changes in the psychological percept with respect to depth perception. Okay? Yes, please, go ahead. Yeah, what actually is different, okay? Why don't we see if we can get into that, questions about what actually is different. I wonder if we might do one more that I think you'll really find fun. And I deliberately withheld this one from you. This is a session where we typically we'll take some photographs and then see what we can do with these photographs. Here's some photographs that I'm going to pass out. This will be one more stereogram. You've been looking at a stereogram. This stereogram was what I did in this classroom in 2009 when I had my 2009 S&P class. And this is, I asked the class to go to the back of the room and pose in 3D, and everybody's got their arms stretched out. And then I took a picture over here and a picture over here, and I've got them this way. I'll ask you to take one and pass it back and around. And then please take your 3D fuser there, which is to say your index card. And, oops, sorry, I was going to hand you my agenda for today. And please try to free fuse that. Sorry about the lockout, Molly. I heard you got locked out of your room.
Yeah, I was in the shower and went back into my room and it was just locked.
Oh my goodness, sorry about that. So please go ahead and use a 3D fuser. That's this index card. Relax your eyes, try to get them to look toward your feet. Thank you, when you have extras, thank you very much. And did Molly get one of these too? Okay. These were just going around as you came in.
Thank you.
Okay.
Is your vision supposed to blur until
I wouldn't call it blurring. Becca's question is, will your vision blur? It might be hard to get these two to fuse, and you might want to create a little bit more distance between your page and yourself. You might keep that index card all the way on your nose, but you can lift your head back a little bit. Hopefully you can get these. So this is a real life picture. Is anybody getting them to fuse? You're not getting that one? Okay. Yeah, I'm an experienced free fuser. I can get it, but it might be that this one is a little too hard. It might be that this image is a little bit too big, too. You know, that you'd have to pull yourself quite a bit further back to get this one to work. I think Yuen's on it. She's got really good distance. Did you get those to come together or not really? No? Okay, why don't we do it this way? I'll invite you to hang on to this one, and as you get better at free fusing it, and it actually is a skill, it's a motor skill, where we have to learn how to dissociate our accommodation Okay, this is how much our lens is bending, from our vergence, and that's how much our eyes are moving inward or outward. And those are two different motor processes, believe it or not. The muscles that are controlling your accommodation and the muscles that are controlling your vergence, they have to work in a way that they don't typically work for these kinds of demos to work. And it does take a little bit of practice. Some images are more easily fused than others. Okay, all right, so that was that. All right, why don't we go on and see if we can understand this a little bit. So Jenny had a question, and that is, why do these things look as they do, right? Okay. And we'll see if we can begin to understand this just a little bit. Before we do that, anybody want to help us with understanding what the geek trick was? We talked about the geek trick, and we've basically already seen an example of that. What was the geek trick? We'll go with Briella this time.
When SMP geeks go on vacation, they take a picture approximately 6.5 centimeters apart, because that's how much your eyes are apart.
Yeah, okay.
And if you're able to fuse them, either using this or like a Photoshop, you can get like a 3D image.
Okay, right. Okay, so we do take a picture here and we take a picture over here. Does anybody have on them maybe an iPhone or something else that takes a picture? Does anybody have some? Okay, could we take a couple of moments and maybe pose for each other, and we'll do the geek tricks, and then maybe you can email the pictures to me if you wouldn't mind. Whoever is near you, we'll just take a couple of pictures, and the idea would be I'll shoot Harshita like this, and then I go 6.5 over here, and we'll shoot like that. And maybe you can get a couple of students to strike a pose that is very depth oriented. Stick your hands out from near to far, hold that pose, freeze it, and click it twice. And we'll see if we can get maybe a better stereogram than the 2009 class had. So who's got the phones? Okay, yeah, and try to keep your camera as stable as possible. Once on the left, and then again on the right.
Do I go over there to do it, or do I just go over there?
So what you would need to do is wherever your picture is, okay, and then you're going to move 6.5 centimeters to your right. Okay, so you should be in the same physical place. Click once, click twice. Okay. Okay, yeah, if you could. Yep. Oh, okay, yeah. Maybe we can would you do it like a group shot or something? Okay. Ta-da! Yeah. Uh-huh. Okay, I wonder if we can do one more. And can we do it this? Well, I'll try to freeze as much as we can. So if you go to your first position, okay, and we're going to freeze at 1, and we're not going to move until she is done with number 2. Okay. Cheese. Don't move. Anybody? Nobody moves. Thank you, Chelsea. All right. Okay, so now maybe it'll turn out to be the case that the 2013 S&P class has the best stereogram going. Okay. All right, really good. So thank you for doing that. And if you want to email any of those to me, I'd be happy to see if we can put them into a PowerPoint. Some of them might work, some of them might not work. Please go ahead, Becca.
What would the results be if you,
If you switch the images? Is that
no, if you were to, you're attempting to take it 6.5 centimeters away.
Yeah.
But you also change the height.
Yeah.
Does
Yeah.
it not work, or is there a weird fusion that happens, or?
Both of those are true. It doesn't work as well. Okay, so everybody in this class has slightly different interpupillary distances, right? And we only take the picture at one particular distance. But that was true over here also, right? That was true for this thing, right? And so what we can say is that if you introduce maybe a vertical shift, you'll probably lessen the effect. But if you're a good free fuser, you might be able to overcome that. Okay, and then also it might be the case that Chelsea actually moved by 6.5 centimeters, but maybe she moved 7, or maybe she moved 9 or 2. There are all kinds of variables that go in there. And with a little bit of practice, you'll find that some people can really free fuse anything. I still benefit by having one of these, but occasionally I can not even use that and just sort of let these images slide together. And I know some people in my field who are really good. They can free fuse anything from any distance. Please go ahead, Brianna.
I took a biology class that we studied stereopsis, and we learned that like some organisms that have eyes that are farther apart typically have better depth perception, but at what point is it like, let's say you're taking a picture, at what point would it be too far apart that it wouldn't work?
Okay, right. So Brielle's question again is, if we look at a different species, then it might have really wide eyes. So some of the great cats, for example, have fantastic eyes. And this is often the case, as you might know, and they might have mentioned this in the biology, of the predators. The predators actually need to judge depth if they're going to survive, and they need to be really, really good at that. The prey animals are probably just more likely to have eyes on the side so they can get this whole view of who's coming at me. And I don't really need to know exactly how far away they are. I just need to know if the bad guy's coming from this distance, I need to go in that direction. Right? So there are these differences. I wonder if I can begin to respond to your question, how far away is too far away? I put it like this. There's really no upper limit on that, and it depends on the range of depth that you need to see. Some people may have taken an astronomy class. Has anybody taken astronomy in here? There are astronomers who will wait for the Earth to be at two different positions in its orbit across 6 months. So it takes 12 months to go all the way around. But what we can do is we can photograph, for example, maybe the moon or some celestial object at this point in our revolution around the sun, and then 6 months later at this point, okay? And that's a really big distance that we can use for this stereopsis, so to speak, right, okay? And then you try to fuse those images and you can pull out some information. And that's about as good as you can do on Earth, right, the full revolution. So I hope that begins to answer the question of how far is too far. There's really no upper limit other than what is practical. Yeah, go ahead, Owen.
Wouldn't it depend on the amount of disparity versus the monocular depth cues?
Okay.
Because,
right.
like after a certain point, if I look at, say, this desk and I keep moving further and further away, originally it would be like I'm closer and closer to the desk, but I feel like after a certain point, the monocular depth cues wouldn't agree with the disparity.
Okay.
And it'd be, I'd have a perception of two different images.
Okay, very good. Okay, so a very complex question. A couple of ideas there. We do have monocular cues that we started out with, right? All of these artists that we had seen, and we also talked about just covering one eye and pulling information out that way. And then you get maybe additional information from binocular disparity or retinal disparity. And generally speaking, in the real world, those two cues will co-vary with each other. You can go into a laboratory and you can systematically manipulate cues in images that have been photoshopped, and you can throw off and put into conflict with one another the disparity cue and the monocular cue, or binocular and monocular cues. You can make them work together or apart from each other. Generally speaking, I think what will usually happen, and this will not always be true, but it will frequently be the case that the monocular cue will win. Okay, and that's, I think, one piece of evidence for that is just the, if you will, clinical observation that a lot of people are walking around and they're driving cars and they don't even know that they don't have stereopsis. Right? They don't know that they're missing that aspect of their vision, and using only monocular cues, they're doing just fine. Right. So I hope that begins to answer your question, that there can be cue conflict, and you could arrange it such that the binocular cues would win, but generally I would guess that the monocular cues would win. Yeah. They're probably evolutionarily older, I might guess. Right? Yeah. Okay. All right. Really good. So we're still trying to make our way back to Jenny's question. So why does this all work? And then we're dealing now with this thing. Who remembers hearing about the horopter? Okay. All right, why don't we see if we can have a student maybe begin to explain to us something about either the horopter or cross disparities or uncrossed disparities. Those are concepts that came up in the video. Why don't we go with Kirsten, then with Becca?
Well, the horopter's just like on the plane of fixation.
Okay.
It's not the fixation point.
Mm-hmm.
So it's kind of like a zero disparity, which is like where there's no retinal disparity.
Okay. And if I can pick up on that, if I can interrupt just for a moment. As Kirsten was saying that to me, she was looking up here, then at one other point she looked at me, and then one other point she looked down at her notes. So she's moving her fixation around. So wherever your fixation is at that moment, that is the plane of zero disparity. Right? We'll be talking about retinal disparities. And as you're just writing things down and looking up at me, again, your fixation is changing on a moment-to-moment basis. So it might even be that you're only getting a few hundred milliseconds at one fixation, and then a few hundred milliseconds at another fixation. Every time you move your eyes, you've got a new fixation point. You're in a new horopter. So that was a really good start. And then I wonder if we can begin to build on that and get to crossed and uncrossed disparities. Anybody want to? We'll go with Becca and then with Owen.
If something in your visual field is in front of the horopter,
What, do you mean nearer to you?
yeah,
Okay,
nearer
thank you.
to
Thank you.
Then that's a crossed disparity because you think that you have to think of it this way: you have to cross your eyes
Okay.
more
Uh-huh.
to fixate on that object, and then if it's beyond the horopter, you're uncrossing, so you're straightening the your eyes.
Yeah, okay, right, you're uncrossing them. So this is we call these vergence eye movements. We might be moving them in or moving them out, right, okay? And we can either converge or diverge, but we call these vergence as the general family, converge and diverge. Did you want to add anything, Owen? Or is that?
Sure. And when you have a cross disparity, when there's a cross disparity, you have a sensation of something being closer to you than your fixation point. And then if you have an uncrossed disparity, then you have a perception of that being further away than your fixation point.
Yeah, right, okay. So for the moment, I'm going to fixate right on Emily, and that's where my fixation is. So she's in my horopter, okay? Now Jenny's going to be, for me, the image of Jenny is creating for my brain and my visual system more specifically, it's creating a cross disparity, and Kirsten's creating an uncrossed disparity. But what I could do is I could now move my eye back to Kirsten, and in this case, Emily, who was at the horopter a moment ago, now she's creating a cross disparity, and Jenny is creating a very, very crossed disparity. Okay, so it's not just that we have crossed or uncrossed, although we do have those categories. There's also existing gradations. Something can be really, really near to you, or just a little bit less near. Okay, so there's this continuum, and that's a good thing, right? Because space itself is a continuum, so we'd expect that the neural response to the environmental stimulus should also be continuous. Was that a question or a comment? Yeah.
Yeah. So I guess this feels like really counterintuitive. Is it that we can perceive the depth of everything except for what we're fixating on?
I wouldn't say, because that's part of this continuum that goes from, we can say that we're going to make an absolute zero at, if I'm looking at Emily, we'll make that the 0 point. And we might say that Kirsten then will be the positive disparities and Jenny will be the negative disparities, might be one of the ways of thinking about that. It doesn't mean that she's not at a particular depth plane, right? She still is in a depth plane, we're just arbitrarily setting that one to 0. And then when I refixate, we reposition the 0 of our continuum. Right? Yeah, great, yeah, really good. Okay, can we all do that together? Can you show me by gesticulation? Let's start out with a fixation like this, okay? All right, a fixation like that, all right. Can you show me how you would get to an uncrossed point? And, okay, so you go ahead and do that. And then if you want to get to a nearer point, you would do what? All right, so that's crossed and uncrossed disparities. Okay, really good. I have to tell you that what's really helpful to me as an instructor is that when everybody in the room has come in and watched the video, you get that right away, and people are able to explain it to each other and to me right away. For the first 10 or 12 years when I was doing this course, it took me the entire session to get people to, to do this properly and to understand what's crossed. I mean, this can be a really intimidating diagram as we build this thing up. We go through these 0 disparity displays, and then we get to here the horopter, and then we get to this one, and I have to tell you what a nightmare it was to do this one in class without anybody having seen it before, and talk about how CPF isn't corresponding here to FPC, right? We have non-corresponding retinal points. Back over here, okay, we had AFG, and then A prime, F prime, G prime. These are corresponding retinal points, okay? And because they're corresponding, there's no mismatch, so there's 0 disparity. And the horopter is the plane of 0 disparity. But as I'm looking at Emily again, we've got Kirsten way back there, we have Jenny, so all kinds of stimuli are creating non-zero disparities. And that might be diagrammed here, CPF, a very different sequence in this eye, and you can see what's near or crossed and what's far or uncrossed. Okay? Right. Please go ahead, Emily.
I might ask about this a couple weeks ago, but was this the kind of phenomenon that explains what's going on in
Oh.
the optical illusion book?
Yes, okay, so the optical illusion books, we sometimes call those the magic eye books. Okay, Christopher Tyler, who works at Smith Kettlewell Eye Institute in San Francisco. I know a lot about Smith Kettlewell because one of my fellow graduate students went to do her postdoc there, and my graduate advisor, Leslie Welch, did her postdoc there. So it was developed at the Smith Kettlewell Institute in San Francisco. And yeah, so what happens is basically you've got an image, and then they overlay that with another one that's offset by just a certain amount. And that might be a very complicated image where I have, for example, if I'm fixating at Kirsten, I can have a duplicate image of Emily, and she would be at a modest near disparity, and then I would have a duplicate image of Jenny, and she would be at an even wider disparity. So you get this really robust depth plane. And it does take a little while to fixate. How many people have worked again with those magic eye books? Does anybody know that you get the 2 fixation dots up there? Does that work? Yeah, okay. That's essentially what we're doing here. You try to get those 2 fixation dots to slide one on top of the next, and that's what we're doing in this demo when we're trying to get them to slide one on top of the next. Just before we lose that skill, I wonder if we can flip over on the page. I should have had us do this a moment ago. But maybe we'll take just one more shot at free fusing. And this one now is looking at some orientational disparities. You'll pull out your index card. We'll give you a moment to do that. Yeah, it's probably better to hold the index card lengthwise so you keep yourself a good distance away. Let your eyes relax. Try to focus on your feet as if you could see through the desk toward your feet. You're looking at a more distant point. Anybody get them to slide on top of each other? Yeah? Okay. And when they did slide, did you get a sense of depth there, that these things were sort of poking out at you? Okay. And yet when you look at either one of them, you don't necessarily, you get a sense of orientational differences, but you don't get a sense of depth differences. Right? Pretty cool. Yeah, it is weird. June said, yeah, that's weird.
It's not as if like for me, it's not as if they're sliding together.
Okay.
It's as if like one, only like something in the lines in the right eye are disappearing.
Okay, it's almost as if one eye's view is dominating the other.
Yeah.
Okay, and what we're going to be talking about in our next session, we'll be talking about the phenomena of binocular rivalry and dominance and suppression. One eye's view might dominate the other. So generally speaking, as I'm looking out over this audience, I have a lot of redundant information in my right eye's view and in my left eye's view, right? But you can imagine that we can go into a laboratory and I can have, for example, my right eye's view as I'm getting it right now, and I can put a picture into my left eye of, say, the Manhattan skyline. Okay, that's a very different image from this image that I have right here. So which of those two views wins? And as we'll see in Friday's session when we talk a little bit about binocular rivalry, actually the brain sometimes will toggle back and forth between those two, giving you sometimes the Manhattan skyline and sometimes what's going on here. And it's a paradigm that's used a lot in neuroscience to figure out the relationship between neuronal firing and perceptual experience. Because you can be hitting one of two buttons. I'm getting the class, I'm getting the Manhattan skyline. The class, the Manhattan skyline, while we're taking MRI information on you. And you can see which neurons are becoming active during which of the two perceptual states, which is pretty interesting. Okay, all right. So let's see if we've gotten back to, we've started to answer Jenny's question, right? So why is it that these things are operating as they are operating? Okay. Okay, see if we can move on then, and we'll do this one. Maybe we won't have a pop quiz today, but we can begin to answer this perhaps by looking at the image that we have here. These images contain no binocular disparity. So I could pick this one up, if it were in PowerPoint, I could slide it over to here, and that triangle would be right on top of this triangle, that circle right on top of that circle, and that cross right on top of that cross. There's zero disparity, right? The two are the same. So given that, let me just ask you this question. Given that there's zero disparity, if we were to free fuse this, if I turned this into a handout and had you use your septum, what would you see here with respect to depth perception in this particular case? Yeah, it'd be flat, right? So actually the fused image would look very much like either the monocular images, right? The fused image would look like either of the monocular ones. Who's following that? Is anybody confused by that? And I think that will be an important first step in answering Jenny's question, right? So there's no disparity here. Now what we want to do is start to mess things up a little bit by creating crossed and uncrossed disparities. Now let's do this again by gesticulation. We've got our two hands out this way, okay? Can somebody tell me how I would create a cross disparity? What would I have to do to my right hand to get a cross disparity? My right hand would have to do what? To the left, okay? Or equivalently, my left hand would do what? To the right, okay. And then if we did have stimuli that were generating these kinds of disparities, those stimuli would look nearer to me than the fixation point would look, right? Because cross disparities look nearer, okay. If we do it the other way, here we start at neutrality, and we take the right eye's view, we step it out to the right side. We take the left eye's view, we step it out to the left side. Now we have uncrossed disparities, and any stimuli out there that are generating that pattern of activity on our nervous system are going to look further away than the point of fixation. And if we move our fixation, then the whole ballgame changes again. But it always plays by the same rules, right? Crossed and uncrossed disparities describe the rules for any given fixation, which might change every couple of 100 milliseconds. But the rules are the same. Go ahead.
How would you relate like uncrossed and cross disparity to changing the actual stimuli?
Okay, so that's our question. What change to the left image would make the circle appear near in depth? So let's let you think about that for a moment, and then we'll have you chime in on that. But we'll see how many people can think that one through. So you might know that inside of PowerPoint, these could be clickable items. I could click on that triangle, I could click on that circle, that cross, and the same thing over here. What might I click on in the left image to make the circle appear near in depth? Okay, Harshita's got an idea. We'll let people think it through. Okay, go ahead, Harshita. Okay, so what I might do is click on this guy, and how many people have done this kind of thing in PowerPoint? You click on him and you get these 4 little points on it. People who are familiar with PowerPoint know you get these 4 little boxes that allow you to grab it, and then I might hit my right arrow key and I might move the circle, which is in my left eye's view, okay, it's on the left side, to the right. So let's see how that works. Let's see if Harshita's got it right. That's in my left side, and I start moving something on my left toward the right. Am I beginning to cross or uncross? Cross, and because I'm crossing, will that be near or far? That's going to be near, so Harshita got that one just right, okay? So we could do it that way. Please go ahead. Yeah.
Would you also be able to move the triangle and the cross to the left and still be able to have the circle?
To the left, okay, yeah, that would.
Yeah.
So yeah, these are all relative, right? And you'll see that over the next couple of them. So here's our next question, for example, right? What change to the right image? So now we're dealing with this guy. What change to the right image would make the triangle appear far in depth? We'll let you think that one through just for a second, but I think Owen's kind of given us the lead on that one. So now we want to make the triangle go far in depth, and we're only allowed, per the rules in the question, to work with the right image. Right? If you think you've got this one, I just want to see how many people are following and who might be lost in all of this. If you think you've got this one, can you raise your hand? So most of us are there, and not all of us are there, but most of us are still, okay? So the challenge here is, we'll see if we can get 100% of the people on board. We want to change something of these 3, right, that's our right-hand image, to make the triangle appear far in depth, okay? So we want to think about what's crossed, what's uncrossed, okay? If you think you've got it, can you raise your hand really high? Okay, and if we're not sure that we've got it, that's okay too. Okay, I think almost everybody is there. Can we yell it out? We would have to do what to the triangle?
To the right.
Whoa, move it to the right. Okay, all right, move it to the right. In the right eye's view, we're uncrossing, and what we know about uncrossed disparities psychologically is that they look further away in depth, right? So this is actually, when we're talking about the disparities, we're almost making a statement about biology. We're talking about the proximal stimulation, right? We're creating a pattern of uncrossed disparities on our nervous system. The psychological consequence of that particular kind of biological stimulation is going to be the perception of greater depth for that stimulus. Yeah, please go ahead.
Could we change size?
Can you change size?
Because things that are closer.
Yeah, right, okay, so there actually are, yeah, this is another, so here I've kept everything the same. We could be using size differences. You can make that a factor. And actually you'll be, if I could expand that triangle, for example, there's a range over which I can expand that and you could still fuse it, and it would still work. At some point, you would begin to get this rivalry, right? Okay, right? And you might have the larger one dominating momentarily and the smaller one dominating. And there are people who get their PhDs in understanding the trade-offs between suppression, binocular rivalry, and fusion. So in these images, everything's fusing. We could make them relatively rivalrous. Okay, just to make sure we're all on track with all of this, I wonder if we can have you think this one through. Describe 2 different ways of making the cross appear near in depth. Again, Owen's question a little while ago was helping us out. So we want the cross to be near to us. Can we get there 2 different ways? Okay. We'll let you think about that just for a moment. And when you think you've got that, can you raise your hand so I can see where people are on all of this? Okay, I think most of us are there. I think Elise had her hand up. Could you help us out, Elise, with...
To make the cross appear nearer, you could either move the one on the left further right,
Okay.
or the one on the right further.
Okay, right. So we just get those. Here we are in the left image, and we're now moving that left target to the right, or over here, the right target to the left. Either of those would do the trick. And that gets back to the comment that Owen was making. So lots of ways of getting there, and lots of different ways of getting there. Okay. All right. It sounds like we've got a pretty good idea about how that's going on. One other thing that I'll add, since we've made really good time going through all of that, and thank you all for watching the videos and bringing your understanding to the classroom, is that we've talked about different properties that these cells in our occipital lobe will have, in area V1, the primary visual cortex, and some of them are tuned, for example, to orientation, right? And some of them are tuned to maybe different patterns of how light is distributed. Some of them might be on center, some of them might be off center. And so forth. Some of them are tuned to lower spatial frequencies. Some of them are tuned to higher spatial frequencies. Some of them are also tuned to binocular disparity. And they fire, show me action potentials, can we all do it? They fire when, for example, there are cross disparities. Okay? And then others are tuned to far disparities. Okay? So the pattern of firing across the area V1 cells will give us some inclination as to how things are laid out there in depth in the real world. So disparity becomes just another feature, kind of like orientation, kind of like spatial frequency. It's not in FAPO, but we do have cells that are tuned to these different disparities. Okay? And if I could say just a little bit more about that, it might be the case that some are tuned to relatively small cross disparities, others are tuned to larger cross disparities, so you can get a whole continuum there. And your perception of depth will be arising from which particular pattern of neurons will be firing the most. Okay, any questions on any of that? More generally, any questions on anything in that PowerPoint presentation? It was about 25 minutes or so. Becca's got a question or comment.
Just to make sure that I understand the bottles.
Good, let's go back to the bottles. Sure.
The statement that the difference between the gaps in the left and right images would occur if the right bottle were nearer than the left bottle.
Yeah.
Is that because the right bottle is in the right side image, the right bottle is slid inward from the left?
Yep.
Okay.
Yeah. And just one other idea about this. I actually didn't use the phrase, and I try not to use the phrase because not everybody is familiar with American football. But in American football, you have to move the ball a certain number of yards. That number is 10 yards. You can think of it as 10 meters before you get another set of tries. We call those downs in American football. And that's kind of like our first down marker. That's the same. That's the first down marker here. Here's the first down marker. You can see over here, this first down marker is arranged in such a way that the two bottles are touching. Over here, you can see that they're actually not touching. So hopefully that makes it clear that that gap, the distance between this bottle and that bottle, is relatively large on the left and smaller on the right. Okay? And so what we've basically done is, in the right eye's view, we've moved the right triangle to the left. Does that work for us? Okay.
So that would be, so moving the right triangle to the left would be the same as moving the camera itself similar to moving the camera itself to the right?
I guess I would put it this way. I would say that this would create for us a cross disparity. This one will look nearer to us, right? Okay? That's probably the cleanest way to think about that.
Okay, thank you.
Okay, great question. Okay, so we'll turn the lights back up. Harsha's got something.
In this, is the only difference between the two that the displacement of the cameras is different?
Yeah, I believe so. Yeah. Now, I don't know if they also happen to move it inward, which they shouldn't have done, but the idea would be, if you really want to make this point well, you just have this thing maybe even on rollers, and it can only move left and right by a specified distance, probably 6.5 centimeters, and that would give you enough to get these two different.
They didn't move the bottles, right?
That's right. Yeah. Yep. Well, I wonder if we can zoom in on this. So she said, but they didn't move the bottles. I wonder if we can go to here. And okay, is this clear? Would people agree that that distance is a little bit smaller than that distance?
Yeah.
How many people would agree with that? Okay. Yeah. Okay. So if it's true that this distance is smaller, it's almost as if we've moved this left oval ever so slightly to the right. Who's okay with that? And if we move something in the left eye rightward, is that crossed or uncrossed?
Crossed.
And if it's crossed, then what happens perceptually? It's nearer. Okay. All right. So is that working for us? Yep. Real good. Real good. Okay. Anything else on this PowerPoint presentation or on binocular? Okay. You've been a great audience. Does everybody have one of these? Now it's time to go to Mars. Okay. We're going to go to Mars. And on this rainy morning, if I can find my Mars presentation, we'll let you put on your glasses. And these are images that have been taken on the surface of Mars. Back in 2004, we had a rover called Opportunity that landed on the surface of Mars. I'll put the lights down. And it went around on the surface of Mars with two cameras. Okay? And one camera is its right eye, the other camera is its left eye, and it had a red filter over one eye and a blue filter over the other eye. So if you could please keep your red filter over your left eye, okay, if you can do it that way, so that's going to be on the window side, and I'll let this roll. And now these are not artist images, these are literally from the planet Mars, and I think I've got each of these going for about 5 seconds. Okay? It might take you a moment to relax your eyes, but hopefully this is working for you. This is 3D, literally from the surface of Mars. After a few minutes, about half the way through, we'll get images that came from a different rover that's on the opposite side of the planet at the same time. And I bet there are even more recent images than these, because we've been to Mars a few times since then. But I think you should feel pretty privileged now, because in the history of humanity, relatively few people have been able to see the three-dimensional view of Mars here on Earth. Okay? And here we have something like, okay, this is Mars Opportunity on January 30th. Some of these work really well. Every once in a while we get a clinker. Doesn't work quite as well. I have trouble interpreting this one, like, making sense out of it. How big are those objects actually? Looks like that might be the parachute that helped this thing land. It has to come down and still function, right? And it's actually slamming into the surface. So here's the Spirit. That's the name of the other rover. There's the Opportunity, and there's the Spirit. And there are just a few more images. There may be 5 or 6 more images, and we'll be done. If you ever want to cheat, you can lift your filters up and just see what it would look like with to your natural eye. You can see the patterns of reds and blues. Right? So everything is kind of, and so maybe this gets back to Emily's question about how does the 3D image work inside of the magic eye. If you flip your glasses up, you can begin to see, what would be happening. A little more distant shot.
I have a question.
Yeah.
I know, when I've been to 3D movies
Yeah.
with these kind of glasses, I always end up getting a little bit of a headache.
Yeah.
Is that because my eyes are being forced to do this free fusion?
Yeah, that's probably it. And the other thing is, Becca, it might be the case that they've basically fixed a disparity for you. I'll call it 6.5. I don't know what they actually used. And maybe you're 6.4, maybe you're 6.9. Okay, so your eyes are actually working differently than they might have in a more typical scenario. So, okay. Wonder if we can do one more. We have only a minute. Okay, sorry to take us away from Mars. Okay. But I tried to, so I go over to the museum called The Works in Newark, and I try to teach about this stuff to young kids. I try to get young kids to understand disparity. Not an easy thing to do. Okay? So I wonder if I can ask you to put on your glasses, and this works best if the blue filter is on the right eye. Maybe everybody's already in that configuration. And let's just see, are you getting some disparity down here for this guy? Yeah, you're getting a pretty good 3D. Who's getting good 3D? Say yes if you got it. Yeah, all right. Now I'm going to try to see if I can get this to work. This is something I've created in PowerPoint. And you've got a vertical stream and you have a horizontal stream. And if you can relax your eyes, it might be that one of those comes out at you by a little bit, maybe. And then hang on, keep on looking at it, and I'm going to change it just ever so slightly. I'm changing the disparity. I'll change the disparity one more time. Okay? Is anybody getting depth here? Okay? And now if you take your glasses off, look, what I'm doing is I've got these kinds of depths. Notice that in one pattern, red is to the right of blue, and over here on the vertical pattern, red is to the left of blue. So one of these should be coming at you and the other one is receding. I'm reversing the disparities. Okay? And then, you can ease this thing in, and now you're reversing the disparities this way. Oops, sorry about that. Okay, we're just about out of time. So thank you all for participating in our 3D demos. Hope you enjoyed those. Look forward to getting any photos you want to send me. It would be wonderful if we can have this class captured in perpetuity for future S&P classes when they're learning about monocular disparity. And I hope that you'll enjoy reading the notes about the Pulfric effect. Okay?
What are those doing? Are they
So everything's still online as it normally would be, right? On Blackboard and on the S drive. Okay? If you would please place the glasses in here. If you could bring back the cards so that next year's S&P class could use those. Thank you.